In 1999, the Mars Climate Orbiter was destined for fame. The first ever interplanetary weather satellite, it was designed to study the climate and atmosphere of the red planet, and among many other things give scientists their first detailed understanding of the distribution of water on the surface. But instead, on September the 23rd, after 4 years of planning and 10 months of interplanetary travel, just as it began to enter the orbit of its planetary host, all contact was lost. Mission control was instantly thrown into confusion. More than $300 million of equipment and hard work had vanished in an instant. What could have gone wrong? An investigation was begun, and on November the 11th, the Mars Climate Orbiter Mishap Investigation Board released their findings. There had been a miscommunication in the units that had been used to calculate orbital insertion. NASA had employed the metric system of kilograms and meters, while an external contractor had used the same numbers but assumed them to be in pounds and feet. The modern scientific world relies on collaboration and, above all else, standardization. Without an absolute to measure against, chaos reigns and orbiters disintegrate. Yet whatever we choose, whether it be inches, kilos, or hours, they are ultimately derived from our own existential experiences. An inch is the breadth of a man's thumb, a kilogram is about the mass of a litre of water, and an hour is a purely subjective division of a day here on Earth. But in the cosmos as a whole, there are no men to measure, there's no water to weigh, and the concept of a day on Earth means very little. How then might an extraterrestrial quantify its world? And how should we quantify the universe in the most objective way possible? This was the question that inspired the famed physicist Max Planck in the final years of the 19th century. The German Nobel Prize winner, a professor at the Friedrich Wilhelm University in Berlin, spent much of his academic career contemplating how the laws of nature could be subdivided and studied on a minute and discrete scale. The key lay in the physical laws of the universe themselves. While the speed that a planet goes around its star may vary, the speed of light from that star does not. While the gravitational pull on a large planet may differ from the gravity on its moon, the gravitational constant that relates mass to weight does not. So, by manipulating mathematics to set these fundamental properties of space and time equal to 1, it is possible to define fundamental units that apply to the cosmos, regardless of where or when you happen to be observing it. In 1899, Planck revealed his calculations to the world. The eponymous Planck length measures a minuscule 1.6 times 10 to the minus 35 meters, a decillionth of a millimeter. Planck time, calculated by dividing the already tiny Planck length by the very large speed of light, is even smaller, a mere 5.4 times 10 to the minus 44 seconds long. So there are more units of Planck time in a single second than seconds that have ever passed. While these quantities may seem unnecessarily and pointlessly small for our brains to comprehend, in the last century they have become invaluable to physicists, chemists, and cosmologists contemplating the remaining mysteries of the universe, giving us the tools to understand space and time on the most vital scale. Because observations of our universe have lent overwhelming support to a once outlandish theory that the entire universe was born some 13.8 billion years ago from a minuscule speck that expanded rapidly, exponentially. The Big Bang. Modern cosmologists have probed further and further back through our universe's long history to try and understand the behavior of matter, energy, and space-time itself during these earliest moments. And they have been remarkably successful, reconstructing events to within just a tiny fraction of a second of the Big Bang. And it is here, at the forefront of cosmological research, that Max Planck's fundamental units come into their own. Arguably the final frontier of Big Bang science, scientists strive to understand what happened when the cosmos was just 1 unit of Planck time long, and when it was just 1 Planck length in diameter. Appropriately, this minuscule moment has become known as the Planck Era, And like other famous frontiers in history, it is a lawless, wild west for modern physics. A place where long-held scientific beliefs snap under the gargantuan pressure of a universe compressed. For in that first moment of existence, our laws of physics break down and reveal a mind-bending world of astonishing possibilities. Before we can comprehend the shattering of those laws, we must first understand what it is that buckles and breaks. In the late 17th century, Isaac Newton published his seminal work, the Principia Mathematica. Within it, he proposed not only his three laws of motion, but also the universal law of gravitation. This simple and elegant calculation related the force of gravity to the masses of two objects, such as a planet and a moon, and the square of the distance between them. This simple relation has become a cornerstone of classical mechanics, and in the intervening centuries has proven remarkably successful at explaining the large-scale motions of all celestial objects. More than 200 years after Newton's Principia, a young man sat doodling in a patent office in Bern in Switzerland, watching the clock count away the final hour of the day. Becoming a patent clerk was not what he had hoped for, but after scraping through school with a reputation for a poor attitude and a failed search for teaching positions, this was one of the few options left to him. But his heart wasn't in it, and even now he sketched tiny model solar systems in the corner of his patent applications, yearning for his true home within his notebooks and personal mathematics. Because, despite his failures as a student, this man was no fool. His attitude may have been bad, but only out of impatience. His mind was alive with the great unanswered questions in physics. His name, of course, was Albert Einstein. In 1905, he definitively threw out the rulebook of classical mechanics in favour of a new theory. This theory, which he called special relativity, described the behaviour of things that travelled close to the speed of light. Fortunately for Einstein, his papers found their way to the desk of Max Planck himself, and with his help was able to leave the life of a patent clerk behind forever. Over the next 10 years, Einstein sought to reconcile gravity with his new framework and the new concepts of space and time that he had established with special relativity. This was no easy task, since Newton's universal law already explained so much. But Einstein kept at it, eventually devising another outlandish theory, which would come to be known as general relativity. The mathematics of general relativity are achingly complex, but Einstein's equations describe a cosmos in which the fabric of space-time itself is affected by the objects within it. Objects with greater mass create curves in space-time. The larger the mass, the greater the curvature. A massive star creates a huge gravity well, and its orbiting planets are trapped circling the curved rim of that well. Subsequent precise measurements and experiments confirmed the validity of this framework, including discrepancies in the orbit of Mercury. By providing the scientific world with a new view on gravity, Einstein paved the way for a truly modern form of physics. More accurate than Newton's classical mechanical approach, these heady concepts of distorted space-time offer a much more precise and predictive toolkit for understanding the cosmos. Solving the equations of general relativity was what allowed the priest, cum physicist Georges Lemaitre to imagine the expansion of the universe from a hot, dense state, laying the foundation for the modern Big Bang theory. But even Einstein's powerful mathematical solutions run into problems when conditions are extreme enough. In black holes, whose mass can exceed that of 100 billion suns concentrated within a single point, the distortion of space-time is so great that even light cannot escape, and eventually his exquisite mathematics breaks down. Physics may speak of infinitely small points or infinitely high densities, but when infinity is involved, mathematical tools can't cope. And this is key, for this troublesome singularity at the center of a black hole is similar to the extremely dense state of the universe during the Planck Era. Very similar. For a fraction of a second, the entire mass of the universe was crammed into a space 100 billion times smaller than a single proton. General relativity can tell us almost everything we want to know about the large-scale gravitational behavior of the universe, but it can't tell us about that first, hyperdense moment. Scientists must look elsewhere for the answers to the Planck mystery. Traditional computers rely on tiny transistors on integrated silicon chips for their computing power. These transistors act like switches that can be either on or off, and by linking millions of them together, they create the base programming for everything that a computer can do. Over the years, engineers have made these transistors ever smaller, shrinking them until they're just 5 nanometers in length, the same as about 10 silicon atoms. With such tiny components, the silicon chips in our PCs, laptops and smartphones are more powerful than ever. But there's a limit to how much further we can go. Any smaller, and once these minuscule, tightly packed transistors are actually put to work, strange things begin to happen. Electrons belonging to a silicon atom on one transistor can suddenly and inexplicably jump to another atom on a neighboring component, disrupting the instructions passing through it. This is just one of the many mysterious behaviors we encounter when we're dealing with the extremely small. As a result, the next generation of computing seeks not to overcome these strange effects, but rather to embrace them. So-called quantum computers encode their information not in silicon transistors, but rather in the weird particles themselves. Individual atoms or electrons have the remarkable ability to inhabit 2 discrete states at once. And quantum computers embrace this by turning them into switches that, like Schrödinger's cat, are simultaneously on and off, until they're not. By understanding and embracing these bizarre behaviors, quantum computing can model and calculate complex and uncertain systems, allowing us to do things that wouldn't be possible even with the most powerful silicon supercomputer. This new age of computing is still in its infancy, but it relies on an entirely new physics framework that is already about 100 years old. The physics of the very small seem to defy our classical experience of the world, but it could hold the key to understanding some of the mysteries of the cosmos, including its very first moments. Around the end of the 19th century, while Planck was considering the fundamental scale of the natural world, his German colleagues and collaborators were trying to understand how matter behaved at these minuscule scales. They postulated that the energy in physical systems, such as light energy moving from a source to a detector, did so in discrete, individual packets, rather than as a continuous stream. Insofar as we experience light, this proposition seems ridiculous. Light behaves just as if it were a wave, reflecting, refracting, spreading out and creating interference patterns just like waves on the ocean's surface. But under certain conditions it can also seemingly behave like a particle. Those particles are what we know as photons. In the now famous double-slit experiment, a beam of light passing through both slits will create an interference pattern on the other side, as would be expected for a wave. But if you detect the light as it passes through the slits, then each individual photon passes through one or the other, not both, as a wave would. Thus, we understand that light can be both a particle and a wave at the same time. Once the particular nature of light had been realized, with photons as the smallest possible individual units of light, physicists had a new way of viewing the physical world. They had succeeded in quantizing light into its component photons. But that wasn't all. Scientists soon realized that not just light, but all matter could be quantized into individual minuscule units called quantum wave functions. based on their specific energy levels. The interaction of these quantum wave functions determine what is and what isn't allowed within the physical world. They are the fundamental mechanism of the universe, the reason that anything is here at all. But just as the solutions to Einstein's general relativity equations led to some mind-bending descriptions of curved spacetime and expanding universes, so too do the principles of quantum mechanics have some bizarre consequences that seem almost magical in the context of our everyday experiences. Quantum tunneling sees electrons spontaneously cross physical barriers that should stop them in their tracks. It's this phenomenon that makes the smallest silicon computer chips behave so strangely, with electrons jumping from transistor to transistor with no apparent cause. Elsewhere, quantum fluctuations describe the tiny random changes in the amount of energy in a space at any one time. This is one of the weird consequences of the so-called uncertainty principle defined by Werner Heisenberg in 1927. He discovered that certain pairs of parameters like speed and location are inextricably and inversely linked. The more precisely we measure one of them, the less sure we are of the other. So we might know how fast an electron is moving, but we can't say for sure where it is in space. Quantum fluctuations are the natural result of the uncertainty inherent in the physical world. On the smallest scale, at a particular point in time, there might or might not be a little extra energy. We can never say for sure. So, researchers seeking to understand quantum mechanics cannot work in absolutes, only probabilities. Of course, these are the sort of problems in quantum mechanics that it would take a quantum computer to solve. Fortunately for gigantic creatures, reality warping quantum effects rarely affect our daily lives, since they are only seen on extremely small scales. But on those scales, this new framework has given us new ways of predicting the behavior of matter and energy. These are the very scales that we find during the Planck Era of our cosmos, and the strange behaviors are what we would expect to encounter when the universe was Planck-sized. But there is still a problem, in the shape of gravity. The Planck universe was so dense that the effects of gravity cannot possibly be ignored, and yet gravity is the domain of general relativity, not quantum mechanics. Physicists have tried for decades to reconcile the two, to write the conclusive final chapter of modern physics that can unite these accurate but incompatible worldviews. And the holy grail of that search, the final key to unlocking the Planck Era, is the theory of quantum gravity. "150 meters beneath the border of France and Switzerland, there is a vast concrete tunnel that, like some monstrous subterranean Ouroboros, leads only back to itself in a ring, 27 kilometers long. The Ouroboros is a fitting analogy for this immense structure, signifying birth and death in an eternal cycle. For this is the Large Hadron Collider, and is the largest experiment modern physicists have yet devised to study some of the smallest phenomena in the universe, and understand the birth and death of the cosmos itself. It is a particle accelerator, using magnetic and electron fields placed at intervals along a huge vacuum-filled tube to accelerate protons and ions almost to the speed of light, before smashing them into one another and then scrambling to interpret patterns among the random subatomic debris. Only with such a huge and complex facility are physicists able to generate the high energies needed to smash particles apart, and search for the smaller units that define all matter. But not even the Large Hadron Collider can solve the mystery of the Planck Era, or help in the search for the hallowed theory of quantum gravity. By their very nature, quantum gravitational effects will only begin to appear at Planck scales. To truly understand them, we need to visualize them, but in order to shatter particles into fragments as small as the Planck length, we need to generate energies far in excess of any that have been realized in the Large Hadron Collider or elsewhere. If we used a particle accelerator, it would need to be scaled up to the size of the entire solar system or larger to generate the required energies. Suffice to say, for now, we must stick to theoretical models. But theoretical modelling can only take us so far. 3 of the 4 major natural forces that permeate the universe, the strong force, the weak force, and the electromagnetic force, can all be effectively described by quantum theory. But gravity cannot. The problem with reconciling the gravitation of general relativity with the quantum behaviour of matter is that the 2 systems, while internally consistent, are fundamentally incompatible with one another. General relativity is principally concerned with modelling curved spacetime, while quantum field theories demand a spacetime that is unilaterally flat. What's more, quantum mechanics say that every particle has its own intrinsic wave function. It is less a point, more a smear, whereas general relativity insists that every particle exerts a gravitational force as a result of its distortion of spacetime. But in extremely compact situations, like during the Planck Era, the particles are packed so closely that their wave function smears begin to overlap, at which point even the meaning of gravity, which notionally lies in the space between them, breaks down. To overcome these fundamental disagreements, theoretical physicists have attempted to define a quantum unit of gravity, a massless messenger particle known as a graviton, which carries gravity just as a photon carries light. But the action of gravity is so weak, relatively speaking, that such a particle would be nigh on impossible to detect. Other theories of quantum gravity describe an entirely new framework that can account for the behaviour of gravity on the quantum scale. One, known as loop quantum gravity, suggests that space is composed of Planck-length scale loops that are woven into an extremely fine network like an eternal hooked rug. Another alternative is M-theory, or superstring theory. This is a favourite among physicists seeking to unite not only general relativity and quantum mechanics, but all modern theories of particle physics under the so-called Standard Model. In it, all-encompassing superstrings in 11 separate dimensions may account for all physical phenomena on all conceivable scales, providing a theory of everything, if we could only wrap our minds around the bulk of multi-dimensional hyperspace. If anything, this is yet another problem for the multitasking quantum computers of the future. Today, physicists worldwide are aggressively attacking the problem of quantum gravity, offering theoretical solutions in the form of gravitons, loop quantum gravity, and superstring theory. But so far, their search for this unifying holy grail has gone unrewarded. We have many ideas of how quantum gravity might work, but little evidence to suggest which, if any, are correct. Yet, it is with this informed speculation, born out of centuries of study by thousands upon thousands of scientific giants, that we can begin to paint a picture of the cosmos in its very first moment. The Princeton University campus sprawls across 500 acres of the New Jersey countryside, surrounded by pine forests and salt marshes. It is some 50 kilometers from the Atlantic coast, but the long beaches of Sandy Hook Bay are a perfect spot for a summer sabbatical, away from the rigors of university research and teaching. So, in the summer of 1955, we can picture the pioneering theoretical physicist John Wheeler walking along the sand, his head full of relativistic theories of light, matter, and gravity. Pausing to look out across the gentle swells of the North Atlantic Ocean, he follows the waves as they mount up towards the shore and then collapse in a turbulent, seething wall of white foam. As the sea foam inches along to overwhelm his feet to the ankles, John considers this as yet another dynamical system that seems to evade description. The bubbles in the foam combine, break, and reform, driven by complex and chaotic force. It would be impossible to predict the configuration from one moment to the next. A tiny spark glimmers in the back of John Wheeler's mind, and he keeps walking. That year, Professor John Wheeler of Princeton University published his theories on gravitational fields, in which he argued that at the very smallest scales, the ability to even define length, time, and energy would be fundamentally compromised by the uncertainty principle of quantum mechanics. Continuous space-time would instead be reduced to an unpredictable quantum foam, which shifted and fluctuated randomly on the smallest possible scales. And this is the scale that defined the beginning of the cosmos. By combining the revelations of the last 100 years in physics, including general relativity, quantum mechanics, and the as-yet unrealized theories of quantum gravity, cosmologists can try to paint a picture of the Planck Era of our universe. And it is a perplexing one, indeed. For the first 10 million trillion trillionth of a second after the Big Bang, the universe is just 10 to the minus 33 meters across, 100 billion times smaller than a proton. Here, since space-time is yet to come into existence, time itself is undefined, and space is ultra-compactified. Superstring theories suggest that at this point the universe exists in no less than 10 dimensions, which would soon collapse into a mere 4. But a multi-dimensional hyperspace is beyond the limits of our visual imagination, and the best impressionist imagery we can conjure is that of John Wheeler's quantum foam. Here, space-time folds and meshes into itself and is meshed into quantum micro-black holes and wormholes. The geometry of space twists and contorts instantaneously and unpredictably, and far-flung regions of space are connected by quantum wormholes and micro-black holes that appear and disappear without warning. The spontaneous appearance and disappearance of gravitons ruled by the uncertainty principle gives space a lumpy and dynamic appearance. There is no cause and effect, and we can suspend all our expectations of normal physical laws, for if anything governs here, it is the weirdness of quantum mechanics. Inexplicable quantum fluctuations, tunneling and entanglement cause space itself to writhe, flicker and glitch like some horribly corrupted simulation. At any one time, the geometry of space is an average of all possible geometries. Theoreticians will never be able to figure out how the history of the universe played out before the end of the Planck Era. It would be like trying to construct a family tree when every human alive on the planet could be your parent. Before long, the randomness becomes overwhelming, the probabilities unfeasibly small. Where theoreticians may soon fail, experimental physicists never stood a chance. Even if we somehow managed to generate the monumental energies required to simulate quantum gravity and the conditions during the Planck Era, the data would be incomprehensible. Colliding gravitons or quantum loops or superstrings are expected to create micro-quantum black holes that would immediately evaporate into a hailstorm of random gravitons. Any detection from such a collision would find it impossible to search for non-random patterns, to even begin to understand what is going on. So, for now, we must be content with the imagery that our current, limited physical frameworks can provide. It may not seem like much, but it is a crowning achievement of modern physics to be able to probe the universe at such minute scales. But perhaps by standing further back, admiring the view and trying to understand the later periods, we may be able to find fingerprints of the perplexing time that came before. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. And we'll see you next time.